Hello my dear student, I am S Pandey of 12th class lecture. Today we are in lecture number 51. Lecture number 51 of chapter 4, Moving Charge and Magnetism. Okay my dear student. We have studied till now the magnetic field due to current carrying circular coil and magnetic field due to straight conductor. Okay, today we will study another case of magnetic field due to circular coil but at the axis. Okay, before starting that, let me solve few more questions. Due to lack of time, I was not able to solve in last lecture, so I am going to discuss today. Here the example. Suppose we are having what we have studied. Let me recall. If of radius r, this is the center, current is flowing in this way. Magnetic field at point O, it is mu naught I by 2r. Yes, it was. And for elemental we have studied mu naught I by 4 pi r into theta. The direction of magnetic field we have studied to find using right hand thumb rule. Curling our forefinger will give the direction of current, then thumb will give the direction of magnetic field. Alright my student? Yes. So let me start today's lecture with this example. This was not the example, actually I was recalling. So here the one conductor through which current is flowing, suppose it is 2I ampere, and a concentric another conductor, alright, through which current is flowing but in opposite manner, it is I ampere. This is of radius r and this is of radius 2r. You have to find net magnetic field at the center. What will be the B net at O? Okay, concentric circles. Now here we have two conductor, two circular coil, so we'll have the two magnetic field also. Due to inner one, that is the smaller loop, we will find the magnetic field, it is downward, and due to this one, the magnetic field current is moving in this direction. So let me curl this forefinger in this way. We find that the magnetic field in upward direction. If upward direction is taken in the positive, then downward will be taken as negative, my dear student. For the upward, I am writing mu naught I, it is 2I, alright, 2I divided by 2r, mu naught I by 2r. So the radius is 2r and 2 twice of 2r minus magnetic field due to the smaller one, it is mu naught I, and I is the current here, by 2r. Radius still r. This 2 will be cancelled out. You can see it is mu naught I by 2r and mu naught I by 2r. Altogether the magnetic field is 0. Alright. This question may be asked in the form, student, if these two conductors are arranged and the current through this conductor is given, what will be the value of current through the smaller loop so that the net field becomes 0? Okay. Then in that case you have to equalize this V net as 0, and you can find out by making this I dash, you will get the answer. That is not the very tough. Okay. Let me give a few homework, the very simple homework of the 51st lecture. This is the first homework. I have not designed this question, my dear students. This question has been asked in board exam. The question I will design, I will tell you. Otherwise, the maximum question I used to give, which has been already asked in examination or I used to find in any books. This is the current I. This is the current I. Look at here. This is a circular coil. This is not the part of this diagram. This is a circular coil and the two conductor, if you will proceed, they will meet at the center, but they are not actually meeting. I'm just giving here the perception. It might be meet at the center. These two conductors are connected and have been connected with some source so that they're producing the current I ampere. This I ampere goes now and leaves the I ampere the same. If this is the angle theta, alright, it is the angle theta. You have to find B net at O. What will be the net current at O if the radius is R? Radius of the conductor is R. This is your first homework. Now let me give you another homework. Suppose you are having a circular conductor. This is also the question has been asked in board exam, and this is going to infinity. That is the very long conductor. Alright, and here a conductor of radius R, circular conductor of radius R, the center is O. From center a conductor, a straight conductor is placed through which current is 6I moving. Alright, 6I is moving, and through this conductor in this pattern current I ampere is moving. I ampere is flowing. The radius is R. What should be the position of this conductor? What should be the separation between the straight conductor and center of this circular conductor? Suppose it is the X. For what value of X? For what value of X? The net magnetic field at point O, due to both the conductor, net magnetic field at point O should be 0. This is the question. I hope you got all the data. I don't think it is incomplete. All the data I have given. I don't have book right now. Was remember this one I have given. Okay, let me rub down. Let me rub this. Now, next, one more example, my dear student. This is the very important and also a very interesting question. Right, this is CW, class 4. We are having two conductors. Suppose one conductor I have been placed like this one and another conductor I have been placed like this one. The current flowing through this conductor is going downward and the current flowing through this conductor is coming upward. Alright. So how I will draw over the board? How I will draw? So I am going to draw this like this way. The dot I have given for the conductor for which the current is moving upward. And here the cross I have been used for the conductor for which the current is moving downward. And the separation between these two conductors is 2A. Alright. From the center at a distance x, this is the distance x, you have to find net magnetic field at this point if both the conductor having the current I. Alright, this is the distance x and this is the 2A, this is the A and this is the A, this is the center point. You have to find net magnetic field at point P, or you can say AO. Alright, yes, this is the point O. What will be the net magnetic field? How you will calculate? Look at here, my dear students. Look at carefully. This is very, very important. Due to this positive, the conductor, this is due to this conductor through which the current is moving upward. What will be the position from this point? The position will be this one, and due to this conductor the position will be this one. We know that if this is the conductor, my dear students, and we wish to find the magnetic field over here, and this is the length, like this one, this is the Z, so this will be the Z. Alright, magnetic field must be perpendicular, either downward or upward. It means due to this conductor, the magnetic field will be perpendicular to this line. Either magnetic field will be, alright, the magnetic field will be perpendicular towards here, or due to this one, the perpendicular either in this direction or in this direction. Alright, so the current is moving downward. Look at here. If current is moving downward, the magnetic field will be at this point, you will find in this direction. So this should be perpendicular to this one, but in this direction. Suppose this is the magnetic field B, and due to this conductor, the current is moving up, so the magnetic field will be in this direction. Suppose this is also B. Let me draw the axis. This is x-axis and this is y-axis. Suppose this is theta and this is also theta. Okay, if this is theta, you can see if this is theta, then this will be the theta. Am I right? Yes, if this is theta, then this will be the theta, and if this is the theta, then this will be the theta. Alright, yes. Now this B has a two component. Now this B has a two component. This is the theta, this is B cos theta, and this is B sin theta, and this B has also two component. This is the theta, so B cos theta and B sin theta. But my dear students, these two are equal and opposite, will cancel out, so the net magnetic field we are having here 2B sin theta, 2B sin theta. Yes, alright. Now the magnetic field due to a straight conductor, what we have studied, if this is of the infinite length, remember this conductor are of infinite length, and magnetic field is mu naught I by 2 pi r. We know that. So the 2, this one, mu naught I by 2 pi r. What is the position? It is Z. Alright, into sine theta. Now look at here. It is 2 will be the cancel out. Mu naught I over pi and Z. What is the value of Z? It is root under x square plus a square. Root under a square plus x square into sine theta. Sine theta, for this triangle, the sine theta will be p by h, and p is a and h is again the Z, that is root under a square plus x square. So we can write here the mu naught IA over, alright, and it is pi times a square plus x square. Alright, and the direction it is along the x-axis, so the net magnetic field will be this one, and this is the answer. So I hope this was not very tough, my dear students. Okay, now we'll proceed for the next topic. It is the magnetic field at the axial point, that is the axis of circular coil, and magnetic dipole moment we will discuss. Alright, so let me wrap this one first. The topic, it is magnetic field due to circular coil at its axis and magnetic dipole moment. Magnetic dipole moment. You should note down this topic. I'll rub this topic after using my these two section of the board. Here, my student, I am going to place a conductor not in this way, but side view. You will be able to see the side view, remember, like this one. If this is the conductor, and I'm trying to explain this particular topic in such a way that you could able to understand clearly, because this is not very tough but little tricky. Student confused to visualize whether this axis is behind the conductor part or before the conductor part. Okay, this is the axis. Now I hope it is very clear. This wire is behind the axis and this wire is above the axis. It means this section is towards you and this section is away from you. Alright, now the direction of current is upward, like this way. I hope it is very clear now. This is the radius of the conductor, it is R, and we have to find the magnetic field suppose at this point. Okay, let me take two elemental section here. Suppose this one, the elemental section, to apply the BS law, and the one elemental section over here. Okay, so we have to find magnetic field. This is the length. Suppose this is DL and this is also DL, that is the elemental length. My dear student, this is our observation point. This is the axis, X and Y. Okay, I have put. Now be careful here, concentrate over here. My dear student, look at here, I'm trying to make this one using a conductor, a wire. I don't have bangles right now, so I've used this wire I found in my campus since construction work is going on, and I was able to find this. Let me, yes, this one. I hope now you would be able to see it clearly. Suppose this is the current carrying conductor. Current is flowing in this direction. Alright, and this particular conductor is this one, and you are looking this conductor is side view, like this way. The axis side view, let me tilt it, and the axis is passing from here. Look at here, the axis is passing from here, like this way. You have to find magnetic field at this point. Okay, at this point you have to find magnetic field. The elemental length we have taken at this point, okay, and at this point at the bottom. The elemental length with this point is making a line like this way. Okay, like this way, this red line. Now when we use Biot-Savart law, let me draw here. If it is the conductor and you have to find magnetic field over here, then it is DL. So DL makes the angle theta. We use ideal sine theta. I hope you remember. And K also. Ideal sine theta by R square. Here theta is the angle with this DL and this R. Alright. So where is this R? Is this one. Suppose this is A. And where is DL? So DL is here. Try to find in this conductor. This is your axis. Alright. And DL is here. So you have made this point. This is not the axis. This one is the axis. Now I have laid this to make this is A. Okay, this is A. You can find the angle between this A and DL. If DL is, let me clarify, if DL is in this direction, okay, in this direction DL, and this is the R, so what will be the angle between DL and R? That is A. This is A and this is DL. So you can see it is the angle 90 degree. Alright, it is the angle, this one is the 90 degree. Okay, because here we will use two angles. That's why I am explaining with the help of this particular conductor. Here you can see this is the DL along the length of the ring, and this is the DL and this is the A. So this angle is 90 degree. Everywhere it will be 90 degree. Na? Try to look at here. If the conductor is being placed like this one, the angle will be 90 degree. If this one is 90 degree, what will be the angle? If you tilt little downward, if this is 90 degree, what will be? 90 degree again, 90 degree again, 90 degree again. Everywhere diameter always makes the 90 degree angle. Diameter always makes with the circumference. It is how much? 90 degree. So it is very clear. If you are moving, it is up. So the angle is not going to be changed. Na? Angle is going to be changed, but with the reference, not with the circumference. This angle remains same always. Alright. Okay. I hope you understand, my dear student. Now, we are going to find here the two angles and we are going to proceed. We took very much time to understand. This angle that DL makes with this one is suppose alpha. Okay, and suppose this angle is theta. This angle is also theta. Okay, due to this elemental length, what will be the direction of this? Was the elemental length. This was the elemental length. Here the two conductor actually. This was the elemental length, and this elemental length is current is going in this direction. Okay, in this direction, and you have to find the magnetic field at the axis here. So you will hold the conductor in this way. Alright, you have to find the magnetic field due to this current. So you will hold the conductor in this way. Current is moving in this direction, and you will try to find out the magnetic field at this end. So you will try to find out the magnetic field since the current is going in this direction, in this direction. Okay, in this direction current is going. So the current is going in this direction, and you will hold this conductor. So you will find, since the current is going this way, so you will find the magnetic field due to this one is perpendicular, and it is in this direction, and due to this elemental section perpendicular to this, it will be in this direction. So this is the dB, and this is also dB. If this is theta, then this will be the 90 minus theta, and this will be the theta. If this is theta, this is 90 minus theta, and this is theta. Alright. Again, my dear students, the current is flowing in this direction. Try to find out. You can visualize yourself by looking. Just hold the conductor, and let's suppose the current is going this direction. What will be the direction of magnetic field? If it is like this one, straight, and the current is going in this direction, you have to find the magnetic field at this point. Okay, then what will be the magnetic field? If current is going in this direction, the magnetic field at this point will be downward. Okay, so I think the magnetic field should be in this direction. I have made wrong. Or I can reverse the direction of current. Due to this one, the magnetic field will be perpendicular downward here, and due to this one, the perpendicular magnetic field will be here. So this is the dB actually. How I get to clarify? This is the DL. Suppose this is the conductor, this one is the conductor. Okay, and this is my DL. So the current is going in this direction, and you have to find the magnetic field at this point. Suppose this point is straight, so current is going in this direction, so the magnetic field will be downward. So the downward will be like here if it is straight, but it has been tilted, so the magnetic field will be also tilted by the same angle. Now if it is theta, you can find, if it is theta, this will be the total 90 minus theta. You have to find the angle and then you will see this is the theta and this is also the theta. Okay, now let me draw this diagram over here. It has two components. Thus dB has one component, dB cos theta, and this one has also the dB cos theta, and the two component along this way, so the 2 dB sin theta directly I'm writing. I hope these two are cancel out. So we are having the net magnetic field, it is B net, it is 2 dB sin theta. Alright, yes. Now using Biot-Savart law, you can write 2 and dB, it is the magnetic field due to the one elemental wire. It is K times mu naught I dl sin phi, this angle. Okay, this is not only the theta. So divided by distance, it is a square. Now it is the dB. Now sin theta, this due to this one, this component. Okay, and you can calculate it. 2 k mu naught, all together it is constant, and sin phi, here the phi is 90 degree. Already we have discussed here the phi is 90 degree, so the sin 90 will be 1. So the dl, and value of sin theta we can put, since this is not variable, this is constant, sin theta due to using this triangle, sin theta will be perpendicular by hypotenuse. It is the perpendicular r, the hypotenuse is a. Okay, so we can write here the r by a already square, so it is aq into dl, and this is b net. In which direction we are getting? Along the I. Now integrate it, you will have the answer. You will have the answer. This is very simple. Now 2k mu naught IR, 2k mu naught IR divided by AQ. A is what? Root under R square plus X square. If it is X, root under R square plus X square whole cube, and DL integrated from, remember this DL is integrated to get the magnetic field due to this half ring, and this will be integrated for the half ring. So the integration should be go from 0 to, for the half ring it is, the length will be pi r. Alright, dl. So you have the value 2k mu naught I r divided by r square plus x square 3 by 2, and it is pi r. All together we can write, it is B is equals to, here the 2 and k, it is mu naught. We have taken here the k and mu naught also. I think mu naught in addition we are taking here the, everywhere k will be mu naught by 4 pi na, so 4 pi. Kindly do the correction. Mu naught by, yes, mu naught I r, and it is pi r, so the pi r square, okay, divided by 4 pi x square plus r square 3 by 2. This one, after cancellation you will get, you can see this pi r square is nothing but the face area of the conductor. So you can write, and 2 will be cancelled out, so you can write mu naught Ia by 2 pi x square plus r square 3 by 2 I cap. This is the magnetic field. This is the magnetic field, my dear students. Okay, now let me do a very simple case in this one, and in next lecture we'll continue from here. Here we are having one coil. Let me use this again. Here I'm having, suppose, one coil and the current is flowing in this direction and the magnetic field is B. Alright, suppose I use another coil and the current is in same pattern, in the same direction. What will be the net magnetic field? It is the 2B. For n turns, how much the magnetic field? It will be n times B. So if n turns will be given to the circular coil, then magnetic field will be, for n turns, okay, we can write here B, it is mu naught Nia divided by 2 pi r square plus x square 3 by 2 I cap. In next class, in next lecture, my dear student, you should remember this equation. We will continue from here. Remember, we will continue from here. Now let me show you the answer for the magnetic field at the center of this coil. Magnetic field at the center of this coil. To get the magnetic field at center, what we have to change, actually this point P will reach to this point O. Suppose this is the center. So at center, although we know the formula, what it is mu naught I by 2R. We will get the same at center. Alright, x tends to be 0. If x will be 0, this point will come to the center. Alright, so you have to put the value of x 0 in all the equation and you'll get the answer, and it is B equals to mu naught I by 2R. Alright, and for n turns you will get the answer. It is n multiplied. Okay, nothing is very difficult, so you can do it by yourself. Okay, my dear student, in next class I will discuss few more very interesting thing. But remember, before starting something new, I will discuss here the magnetic dipole moment, as I have told you to discuss. Okay, one numerical I am giving you for your homework. One conductor, it is radius r and it is 2r. Alright, yes, 2r. And another conductor, this one, and the radius again r, and the distance it is 2r. At this point O, you have to find the net magnetic field. BO will be what? If the current is in this direction, I, and in this direction current is I. Let me tell you the direction of current. Be careful over here. If you are looking from above, okay, if you are looking from above, the current you are looking clockwise. Alright, now in this, if you are looking from here, you will see the current is clockwise. Okay, because it is very difficult in this three-dimensional, that's why I have told here, if you will see the conductor and from here it is clockwise, and for this one, if you are looking from here, it is clockwise. Alright, now you have to find the direction magnitude. Actually this question has been asked in a very famous examination. You have to find the magnitude as well as direction of net magnetic field, and I'm asking you to find the net magnetic field at point O due to this combination, and this is the 90 degree. The angle between these two lines is 90 degree. Okay, so this is all about today's lecture, my dear students. Thank you very much.